definitely. Thanks.
So when people join in, how do we know they're listening and can hear us and things?
We don't until they start getting on.
Okay.
I mean, we've got, you can see the attendee list. If you hit that, and it'll show you who's on.
Okay.
And basically, when people start logging on, you'll hear a beep.
Okay.
Actually, people have tended to get on just a hair late.
I see. So I don't need to do anything to share the video. It's up now, and they should be able to see.
Yep. There's a couple people.
Yeah.
Yeah. So everybody that's on the attendee list should be able to view the PowerPoint right now.
Okay, great.
Who do we have joining us?
Donna Ostenberg.
Good morning.
Good morning.
This is Kevin and Spooner.
Oh, hi, Kevin. I see you're not online yet.
No, I do this backwards. I'm working on it.
Okay.
Richard Lupka in Clark County.
All right. Yeah, Eric, we should have about a dozen people this morning.
Okay.
The first one we had about 25, but since then we've been averaging about a dozen.
Okay.
And there's been some people that haven't been able to get on because of conflicts, but the thing is recorded, so after it's over, they can access the recording and hear it just like they were online.
Okay.
Yep, we lost Donna.
I've been disconnected. I'm trying to rejoin. I'm here still listening.
Well, we'll give it a minute or two more and see. Kevin, you still having problems getting on?
Well, I'm still waiting. I just finished the login, so
Okay.
it just says you are now connecting to the meeting.
Okay, so you should be up in a minute here. Well, why don't we get going here, Eric?
Okay.
So this morning we have our last webinar on energy efficient greenhouse production, and we've got Eric Runkel from Michigan State Horticulture Department. So this is kind of his specialty area, so we got him to be part of this grant to do that. So why don't I let you take it over, and then at the after this is over, I'll get the presentation put up online and speaker notes and evaluation.
Great.
So appreciate it.
Thanks, Scott.
Go ahead.
Good morning, everyone. We've, for the first time in quite a long time, had some technical difficulties here at Michigan State where our internet was down for about an hour and a half. Fortunately, it just came online about 10 minutes ago. So if for some reason, I don't anticipate there being a phone problem, but if for some reason I'm able to advance the slides, then we may have a couple-minute delay while Scott has to log in as a presenter. So can you all hear me okay? I will assume that is a positive.
Sounds good on my end.
Okay, thanks. Okay, so let's go ahead and get started. As you can see, we've got a number of slides to go through, and I'm guessing some of this will be overlap, but basically the factors I'm going to talk about this morning are looking at crop culture strategies to produce crops more efficiently, thereby reducing the amount of energy consumed in a greenhouse. So this is work that mostly has been generated at Michigan State, and you can see my co-author is Matthew Blanchard, who just finished his PhD, and some of his research is then incorporated into this presentation. Let's see, I'm trying to advance the slide here. What's the magic thing here, Scott, to move to the next slide? Doing that before.
Lower left corner.
There we go. Okay. Okay, so I think a lot of you have a sense of greenhouse production. About half of the bedding plants, about half of the floriculture crop production in the United States is on bedding plants. And of course, bedding plants are plants that are intended for the garden to be planted outside once it's warm enough outdoors. And so usually that market for us is about the month of May, although it's not uncommon for growers to produce plants in the north and then ship them in the south when they can be sold much earlier. In fact, we have some growers in Michigan, and I'm sure some in Wisconsin that will be shipping products down south in the month of February and into March. So during this period of time, we're heating greenhouses when, of course, it's coldest outside, and you've probably heard already, but estimates for heating costs are about 10 to 15% of the total greenhouse production cost. So one of the reasons we're interested in this topic is the volatility that we've seen in the price of fuel costs. This is the price of natural gas adjusted for inflation. Fortunately, natural gas has come down dramatically this year, but I think many people would argue that that's probably not a long-term trend, that we're probably going to continue to see relatively high fuel costs. So if you look at what's happened since the turn of the century, we've had a pretty dramatic increase in fuel costs. Again, it's down right now, but we expect costs will probably increase once again. So when we look at the cost of energy and when you survey greenhouse growers, certainly energy cost is one of their biggest concerns. Labor is something also that's a concern, but energy is something that we have the ability to have an impact on. And so, as I mentioned at the beginning, there are different ways to improve production efficiency. Basically, the goal is to produce crops in a relatively short period of time so that they're basically the time once they enter the greenhouse until they're finished is reduced, and at the same time you don't want to marginalize the quality of the plants. Now, a challenge for growers is that pretty much everyone in the United States grows dozens, if not scores or hundreds of different varieties. And as you may know, not all plants respond the same way. And so what we've needed to do is to basically get an understanding of how different crops respond. And really we've needed data on each crop species because not all two crops respond the same. So the three main areas I'm going to talk about, first of all, are using supplemental lighting. So we're talking high intensity lighting, typically from high pressure sodium lamps, and using them on young plants, whether they're seedling plugs or liners as basically a rooted cutting. And the reason why we're interested in lighting at that aspect is that the relative cost on a per plant basis is low. The second item is looking at how photoperiod influences flowering of some of these plants. And again, we're going to emphasize bedding plants, but there are a number of other ornamental crops that have a photoperiod response. And then the last one would be looking at how temperature influences crop timing and how temperature then influences the amount of energy that's consumed at different production schedules in different locations. So let's first look at supplemental lighting on plugs or transplants. So we're talking basically young plants, plants that are during the propagation stage. So a little bit of an overview about light, and I apologize if this is a little bit redundant, but light is actually a rather complex phenomenon. And the more people understand light, the more questions they have. But basically light can be broken down into its three dimensions. First of all, and probably what we're most familiar with is the intensity of light, which is sometimes called light quantity. And that primarily influences photosynthesis. So photosynthesis then influences basically the amount of plant dry matter that accumulates. It's basically how much carbon does the plant accumulate, and for a lot of plants that's a function of how much light it receives. The second dimension is the light quality, or the spectral distribution of light. In other words, how much red or how much far red light does a plant receive? And one of the items that influences is extension growth, or plant elongation. So plants grown under certain wavelengths of light will be shorter than other wavelengths of light. And then the third is the duration of light provided each day, which is often referred to as the photoperiod, or the day length. And that's basically how much light is there from a little bit before sunrise until a little bit after sunset. And as I said earlier, that's important because many of the floriculture crops that we grow flower in response to that day length. So a little bit about light quantity. We know that the growth and yield of most crops is influenced by how much light the plant receives over a period of time. Now, the most common way that we describe light is basically how much light is received during the course of a day. And we use the term daily light integral, which will often abbreviate DLI. And that's, again, basically counting how much light do we receive during the course of a 24-hour period. And the units that you'll see basically is the number of moles of photons. So photons are basically little particles we cannot see, but they're little particles or packets of energy. And it's basically how many of these photons do we receive in a square meter of area per day. So an easy way to understand what a daily light integral is to use an analogy of a rain gauge. So when we are interested in measuring how much rain we receive, we're usually not interested in how much rain are we receiving per second. It's more how much rain do we receive in a day. And so when we measure the daily light integral and try to describe the light quantity, basically we use a sensor that calculates the intensity over a period of time and then integrates those values to get a sum of how much light is received. So if you think of it again as a rain gauge, we have a similar concept of how many photons of light within that photosynthetic wave band 400 to 700 nanometers. How many of those photons are falling within that square meter of space? So light changes dramatically depending upon location and time of year, as well as greenhouse characteristics. You can see online what some outdoor values are in terms of how much light is received on average in the units, again, are moles of photons per square meter per day. So it's not surprising that in December and January, when the days are shortest and when the angle of the sun is low, we are receiving 5 to perhaps 15 moles of light, also depending on whether we have a cloudy day or not. And as you travel farther south, of course, the days are longer during the winter and the angle of the sun is higher, and so people receive more light. Now, I have data here just for 4 months of the year, and that's because basically, at least in the north, we're in a light-limiting situation during the winter. And once we get into March, for most crops, the advantages of increasing the amount of light to plants really begins to diminish. So these are values for basically how much is delivered outdoors. Of course, we only get a fraction of that inside a greenhouse, and a common value that we use for light transmission through the structure, through the glazing, if they have hanging baskets, other obstacles, basically we'll get 50 to 60% of that light outdoors delivered to the plant. And in fact, 50% is a common value that's used. And so you can see that we're in a light-limiting situation, which I would define as anything less than about 12 moles of light through the month of February in the north, and even in some locations you can see around the Great Lakes area, even into the month of March. So these are the different factors that influence daylight integral in greenhouses. Of course, the time of year and the location, like we just saw. Clouds, of course, the type of greenhouse glazing structure, the type of greenhouse glazing, whether or not people are using whitewash or shade curtains, and so we would hope that there was no whitewash on greenhouses this time of year, especially in the north. Structure or obstructions, and a temptation for growers is to pack as many plants into a greenhouse as possible, including hanging baskets, and many times growers don't think about what's happening to plants underneath the hanging baskets, and of course those can reduce light intensity quite dramatically. And really the only thing we can do to add light is to use supplemental lighting. Now there are some types of glazing materials that you may have talked about already that have retractable roofs. Here's an example of what we might call a Cravo house, where when the temperatures are favorable during the day, growers can open up the roofs and increase the amount of light that's provided directly to the plants. And so in some cases in the spring, you can have a very high light environment, which generally has a very good effect on the quality of the plants. And then the other extreme is you can have a very shaded environment where you might have a couple layers or sometimes even 3 layers of poly, and then a dense layer of hanging baskets overhead crops. And so we can experience a wide variety of light conditions in greenhouses. So to get a little bit better sense of how light changes during the course of the year, this is assuming a pretty high light transmission, something we might see in a glass glazed greenhouse, for example. And these are values in the Midwest of what we would receive inside. So we're looking at anywhere from about 6 or 7 moles of light on average in the winter, up to potentially near 30 moles of light in the summer. But again, if we pick a value as 12 moles as a minimum desirable amount of light, you can see we're below that value through most of February, and then starting up again beginning late part of October. Now, how do plants respond to these changes in light? Well, compared to a low daily light integral, you can see a little bit of a cartoon there where you see higher light, you get smaller but thicker leaves. You generally get more and larger flowers. The development of a plant is often faster, and that's at least partly due to an increase in the temperature. by basically from the energy provided by the lamps. We get better branching with highlight, thicker stems, and much better rooting. So looking at rooting, this time of year, growers are starting to fill their greenhouses with young plants. They will often receive unrooted cuttings and place them in a propagation house. And this is some work that we did that looked at the effect of the average daily light integral on the rooting, in this case, of a petunia. So basically, petunias were put into a propagation house, provided different levels of shading, and then after 16 days, you can see they were taken out of the media and photographs were taken. And we've done this for a number of plants, and as you can see, as you increase the amount of light provided to that plant, you get a better rooted plant. And of course, anytime you can stimulate, in this case, rooting of a cutting, or you can reduce the time for a particular process in a greenhouse, those are generally a good thing to do. We've also done similar types of work looking at daily light integral on seedlings. So we've grown different types of bedding plants under what we would consider to be a type of cloudy day like we're experiencing in Michigan today. 4 moles of light, 7 moles of light might be a partly cloudy day in the winter, and then 14 moles of light, which would be probably a mid-spring day, a relatively bright day maybe in the month of March. And as you can see, for the plants that we've studied, you have a better developed seedling and a much more developed root system under the highlight conditions. So we've quantified this, sometimes a little bit ad nauseum, but one of the questions we had was, is there an advantage to providing highlight to a seedling after that seedling is transplanted into its final container? So there are generally 2 distinct phases of floriculture crop production. One is basically the propagation stage, which would be establishing seedlings or rooting cuttings. And then the second stage would be the finish stage, which is when those young plants are transplanted into their final containers and usually grown until they are in flower. So what we did is we grew different young plants under different amounts of light, and then we, after a period of time when we considered them ready for transplant, we moved them into a common environment and looked at how long they took to flower. So what we have here is a graph that demonstrates the effect of daily light integral on the subsequent time to flower. In this case, we just chose Celosia as a representative plant. So the graph shows you the daily light integral, which is here on the x-axis, and the days to flower here on the y-axis. And as you can see, under a low light condition, we're taking plants about 43 days to flower, and then as you increase the daily light integral, we saw progressively faster flowering. So one of the things we looked at then was why are plants flowering faster? And we actually found that plants developed fewer leaves when they were grown under higher light before the first flower was developed. So under low light conditions, plants developed about 23 leaves on average, and under higher light conditions, they developed fewer leaves, and that's at least part of the reason why they flowered earlier. So this is with Celosia, and we have seen that with several other plants. So the most common way that high-intensity lighting is provided is with high-pressure sodium lamps, and that's what we mean by the HPS. We see that when you provide supplemental lighting until about March, you get an increase in the dry mass, meaning that the quality of the seedling or the cutting is higher. If you're growing a liner, you'll have a more pullable plug for transplanting, meaning that you can basically transplant it earlier. Certainly the heat from the lamps, although lamps, you generally don't buy them because they are inefficient and they output a lot of heat, that can be an advantage in terms of increasing the temperature of the plant. And then as I just showed you, when plants are grown under higher light, they typically will flower faster when they're in their final environment. So these are some general supplemental lighting guidelines. If someone was to contact you about adding supplemental lighting Certainly the time of year is important, so we recommend supplemental lighting from basically from November through the early part of March. Of course, lighting is a cumulative process, so both the instantaneous value of light and the amount of time that you're lighting, the lighting duration, are important. High-pressure sodium lamps are still the most efficient lamp type. LEDs are increasingly being developed. In fact, that's a project that we are working on and have plans to do more on in the future. But at least at this point, the economics are not favorable for LEDs. In fact, one of the challenges that I have with companies is that they'll often report these very interesting numbers that makes them sound like that they're obvious choices for greenhouse production. But many of the times they will not tell you what the intensity is and how that compares under a traditional high-pressure sodium lamp. So the challenge there is to compare apples to apples, basically. So when we're looking at supplemental lighting, a typical value of what's provided is between 300 to 600 foot candles of supplemental lighting, with most common being about 400 to 500 foot candles. Now, foot candle is the most common light unit that growers use. So sometimes engineers will use watts per square meter. Plant scientists will use micromoles per square meter and second. But if you use those to a grower, they'll probably look at you and not have a sense of what that means. Okay, so that's just a little bit about supplemental lighting on young plants. Again, we see it having advantages because the cost to provide that supplemental light to a young plant is relatively small. And we've done some very simple cost-benefit analysis to supplemental lighting and the effect on higher plant quality and faster crop timing with lights. And generally, there is a cost-benefit that's favorable with the high-intensity lights. Any questions maybe before I proceed on to the next topic?
With foot candles, how does that compare to your moles?
So foot candles are an instantaneous measurement. And unfortunately, there's no way you can convert an instantaneous measurement to a mole of light because that's a cumulative amount.
But if I have 600 foot candles for 12 hours, how many moles is that?
Well, I could do the calculation for you. So what we would do is convert 600 foot candles into micromoles. What is that? 7? Do you know offhand, Scott? Is that 7 foot candle? Excuse me, that's not right.
I don't know the conversion right off. I could look it up while you're talking.
Yeah, I think it's about 7 foot candles per micromole. So let's take that 600 and divide it by 7, and that's about 85 that sounds right, 85 micromoles per meter squared in second. Okay. So you said for 12 hours?
Yep.
Okay, so you'd multiply the 85 by 60 to get how many seconds in a minute, by 60 again for how many minutes are in an hour, and then by 12 for 12 hours, and then basically there you have micromoles. How many micromoles do you deliver during the day? There are 1 million micromoles in a mole, so you would then take that value and divide it by 1 million, and you would get 3.7 moles per square meter per day.
Great, thanks.
So 3.7 moles does not sound like a lot, but if you only had 3 moles of light to begin with, you've obviously more than doubled your light.
Yeah.
Good question. Any other questions? Okay. Let's talk a little bit about controlling photoperiod. And again, the goal is to produce these plants in a relatively quick period of time. We know that flowering of many greenhouse crops is regulated or influenced by the day length. The production time can be either positively or negatively influenced by that photoperiod that's provided to plants. And so therefore, if we provide that appropriate photoperiod, we can reduce production time. So there are basically 5 general responses or response categories that plants have to photoperiod, and I'm going to go through each of these briefly. We first of all have obligate short day plants, and those are plants that basically will not flower unless they're provided with a short day. We have facultative short day plants, meaning that they will eventually flower under long days, but they flower faster under short days. Day neutral plants are those in which flowering is not regulated by photoperiod, so they flower in the same time under short days as they do under long days. And then we have obligate and facultative long day plants. So obligate long day plants require long days or they will not flower, whereas facultative plants, long day plants, flower faster when provided under long days, but they will eventually flower under short days. So a very common obligate short day plant is poinsettia. These plants typically only flower under a photoperiod of about 12 or maybe 12 and a half hours or less. And so that's why we get natural flowering of poinsettia. Induction usually begins latter part of September when our day length is, in this case, it's about 12 hours and 20 minutes. Once it's less than that, then the flower induction process begins. And if you're to provide a small amount of light during that otherwise dark period, you would get a delay or perhaps even a complete inhibition of flowering of a poinsettia. This is a photograph of chrysanthemum, and I think many of you know that chrysanthemum, to an extent, is a short day plant. Some chrysanthemums have a very strong photoperiod response, like you see in this pot mum, whereas other chrysanthemums have more of a facultative response, meaning that they will flower under long days, but again, they'll still flower fastest under short days. So we then have facultative short day plants, again, those that flower earlier under a short photoperiod compared to a longer one. This is a kind of a neat photograph showing the effect of photoperiod on growth and flowering of Dahlia. And we can see a couple things going on in this photograph. What we have here is the number of hours of light on a basically in a 24-hour period. We have 10 hours on the left, increasing up to 16 hours, which is about our longest day here in the north in the summer. We have another treatment with continuous light, 24 hours. And then we have something I'm going to talk more about, what's called a 4-hour night interruption. And 4-hour night interruption is basically where we turn on lights from about 10 p.m. to 2 a.m. and basically interrupt that dark period. And as you can see, for this plant and for pretty much every plant we've studied, this is a successful strategy to interrupt the long night. So what do we see in the response to photoperiod in these plants? Well, on the left you can see that plants under short days, these have been in flower, they did not develop too many leaves before they flowered, and then as that day length increased, the flowering was progressively delayed. In fact, plants under continuous light at this point are not even showing flower buds. Now another thing which is not usual, this is kind of atypical, but you can also see the effect of photoperiod on the tuberization process. And so what happens when dahlias are grown under these short days is they flower rapidly, but a lot of that energy then is basically to develop that tuber. And then once you get to about a 14-hour day, you can see there's no tuberization. So there are things that photoperiod can regulate above the soil level, and that's generally what we're most interested in. But here you can see there can be things happening below the soil as well. So this is a photograph. We're basically going to give you some examples of some of these other responses. Here we have zinnia. This is a photo from the University of Minnesota. They've done a fair amount of photoperiod work and grown plants under a combination of different photoperiods and different light intensities provided in growth chambers. So you can see zinnia on the top 4 plants are all in flower faster under short days compared to below, which is long days. And then the other thing that you see is that as you increase the light intensity, the flowering was progressively faster, as well as the quality of the flowers was generally improved. So that's typically a trend, as you'll see some interaction with the effect of light intensity and photoperiod on flowering of a particular crop. So what we've done is basically looked at research that we and others have done to categorize these plants based upon their flowering response to photoperiod. looking just at bedding plants for now, you can see these are some common short day plants, things that include African marigold, cosmos, and the zinnia that we just showed you. Now, a challenge is that sometimes the same species will have different responses to photoperiod. So there are some examples now where some zinnias have a facultative short day response, which is what the F represents, whereas other zinnias are essentially day neutral. So sometimes the lines between these categories are blurring because of breeding efforts. Then we have these day neutral plants. As I mentioned, these are relatively insensitive to photoperiod with respect to flowering, and so they flower at about the same time. And so for these plants, whatever photoperiod you provide really has no effect, and so there would really be no reason to provide artificial long days. Now, Impatiens is an example of a day neutral plant, and yet it might be confusing because when you look at the slide, you see that there's faster flowering under the highlight long day environment. Well, what's actually happening here is if we compare a response, short days versus long days, and this is ambient light, so relatively low light conditions, we can see that basically there are flower buds here and here. But the reason we get progressively faster flowering under the long day is not the actual long day itself, it's because we're providing a higher light intensity. So the higher light intensity provided for a longer period of time, like we are, that high light intensity is here delivered for 18 hours versus 8 hours here, we're just getting greater photosynthesis, we're getting probably a warmer plant, and therefore we're getting a faster plant development rate as a function of the higher intensity and the number of hours provided to that plant. Scabiosa is a herbaceous perennial that shows basically, regardless of the day length, all of the plants are in flower. In this case, the plants received a period of cold, which is typically done with perennials in the winter, and then after 4 weeks in a warm greenhouse, photoperiods from 10 hours increasing up to 24 hours. They're all essentially in flower, as well as plants under that 4-hour night interruption that I talked about earlier. Now, what's interesting to note, and what we see with a lot of plants, is that the plants get progressively taller as the day length increases. And this is at least partly because we use incandescent lamps to provide these long days, and incandescent lamps, we know, cause a lot of plant stretch. And so the more hours of light that you use with incandescents, the taller that they become. So these are some examples of some common bedding plants that are day neutral. Again, so there would be really no benefit to manipulating the photoperiod for these plants. And some of the most common ones here are the French marigold, geranium, impatiens, and New Guinea impatiens. And then most vegetable transplants are also day neutral. And then we have our different long day plants. Again, obligate long day plants are those that require long days or they will not flower. And a long day varies from one crop to another, but the majority of long day plants we've studied, once you get to about 14 hours, that's long enough to induce flowering relatively rapidly. So here's a very strong response to photoperiod. This is a Rudbeckia. This happens to be a perennial plant, but we've also looked at annual plants, and they have a very similar response, where you grow the plant under 13 hours of light or less, and they stay as basically a rosette. And once you put the plant under 14 hours or longer, or that night interruption, you can see the plant has induced a flower. There can be a very strong response between, in this case, 13 and 14 hours, and whether that triggers flowering or not. Similar photograph we saw before. This is a wave petunia that's very sensitive to photoperiod. And even at higher light intensities, if it's a short day, they'll remain vegetative, whereas if you give them long days, regardless of the intensity, they will flower. And then we have the facultative long day plants. Again, they flower faster under a long day compared to a short day. Pansy is a good example of this type of plant, at least a lot of varieties. Flowering is delayed and relatively not uniform under a photoperiod of 14 hours or less. And then once you get to 16 hours or longer, or that night interruption, you get faster flowering. And as you can see, there are quite a few examples of common bedding plants that respond to long days. Some, again, have a facultative response, which is what the F indicates, and then those with an O have an obligate response in that they require long days for flowering. That's just basically a partial list of some of the floriculture crops that are commonly grown. This is a website where basically we have compiled information from our research as well as that from other academics, including Scott. And we have a section on greenhouse lighting, and on that tab, if you click that, there's a document that provides the photoperiod response for a wider range of crops. So let's talk a little bit about manipulating photoperiods. So we know that plants respond to the day length. Now, what can we do so that the response is to the advantage of the growers? Well, of course, the first thing to do is to understand what our natural photoperiod is. So let's take the example of, let's say that we're in the middle part of Wisconsin, 45 degrees north latitude, and we know that the day length depends upon the latitude and the time of year. So what we have here then, the line closest would be if we were in Madison, which is the brownish line. You can see that basically this is the natural photoperiod, which we would define as basically about 20 minutes before sunrise to about 20 minutes after sunset. And the reason we don't use sunrise to sunset data is that we know, just like humans, plants can perceive light before the sun is actually above the horizon. So we'll see that our shortest days in the middle part of Wisconsin are about 9.5 hours in the shortest days of the year, and then that photoperiod increases to our longest day, which is just a bit over 16 hours in the middle of the summer. That's the sort of range that we're seeing naturally. So most long day plants will basically flower fastest with a photoperiod of at least 14 hours. So that would mean if we're trying to produce these long day plants, we would need to provide artificial lighting basically beginning around the first part of September all the way through the winter, and then all the way into the spring until we get a natural photoperiod that is naturally at least 14 hours. So in this case, we would be providing low-intensity photoperiod lighting to these plants until pretty much the middle part of April. Now, if we look at what period of time is a short day occur naturally, if, again, we pick a short day as 12 hours or less, that means that we need to somehow provide artificial short days from about the first part of March all the way through about the first part of October. So that means that we would have to try to exclude some light from plants so that they don't receive light longer than about 12 hours. So how do we create long days? Well, there are many different strategies that can be used successfully, and of course they have their own advantages and disadvantages. The most common is to use incandescent lamps as a night break, meaning that they would be turned on during the middle of the night for typically 4 hours. Alternatively, lights can be turned on at the end of the day, and we would call that day extension lighting. So basically the lights would turn on about sunset or a little after sunset and then stay on until the desired photoperiod was achieved. Sometimes growers will use supplemental high-pressure sodium lamps. So instead of providing a high intensity, they may space lamps far apart. And then a fourth strategy would be something where light is delivered on an intermittent basis. So we would call that cyclic lighting. And ways to deliver cyclic lighting would be to mount lamps on a boom, and I'll show you a photo of that here in a minute, to turn incandescent lamps on or off, or to use a device called the beam flicker. And that's basically a product name, which is a high-pressure sodium lamp with a reflector that rotates to move the light across a certain area. So night interruption, as I said, is the most commonly used strategy to provide long days. Here you can see this is a farm actually in South America where they want to provide long days to keep these plants vegetative. And so a common strategy is to provide light during the middle of the night to interrupt the otherwise dark period. So we've done work looking at how long of a night interruption is needed, how long does light need to be provided to basically stimulate flowering for a long day plant. What we have here is a campanula, which is an obligate long day plant, and then campanula was provided with no night interruption, or a night interruption that varied from half an hour increasing up to 4 hours of light. And as we can see that as we increased the duration of this night interruption lighting, we got basically faster flowering. And we've done other research that has gone longer than 4 hours, but basically once we're at about 4 hours, we're saturating the response. Now this photograph also shows a cyclic lighting treatment where lights are only on for a period of time during this 4-hour period. So in this case, lights were turned off and on so that they were on only 10% of the time or 20% of the time. And you can see that 10% of the time was not sufficient, whereas in this case 20% was relatively effective, but still not as effective as if we had the lamps on the whole time. So some advantages of incandescent lamps is that they're a compact light source, they're very inexpensive and easy to install. The bulb life is not affected by the number of times it starts and stops, which is good if you want to be turning lights on and off. And for these reasons, they're most commonly used for photoperiod lighting. Of course, they also have their disadvantages. We know that they are the most inefficient common lamp at converting electricity into light. And therefore, basically, heavy wiring installation is needed to deliver that light over a particular area. And then something I mentioned with the scabiosa before is that the ratio of red to far red light, the spectrum of that light, has an effect at stimulating stem extension, which in the production of a lot of plants is undesirable. Of course, there are some cases where we do want tall plants, like if we were producing cut flowers. But in most cases, if we're producing a potted plant or something in a container, growers use strategies to try to keep plants short and compact. So this would be a typical installation. You can see the arrows pointing to these different incandescent lamps. These will be typically 60 or 100 watts, spaced 4 to 6 feet apart. And the goal is to provide a minimum of 10-foot candles of light. So the night interruption, as I showed you earlier, can also be delivered in a cyclic manner, where it's on for 6 minutes every half an hour. And this is basically the 20% cyclic lighting strategy. In most cases, it's effective, but as I said before, not as effective as if the light was provided continuously. So this is a diagram of what a cyclic strategy might look like. Here we have a continuous 4-hour night interruption, whereas down here we have our cyclic lighting strategy, where basically we're turning on and off the lamps during that 4-hour period. So cyclic lighting is generally used more to inhibit flowering on short day plants than it is to promote flowering of long day plants. And the reason why is that generally short day plants are more sensitive to light than a long day plant is. Having said all this, when we're looking at stimulating flowering of long day plants, we're generally most interested in basically continuous night break lighting as an insurance for a very strong flowering response. Here's an example of high-intensity lighting from high-pressure sodium lamps. This is to campanula, which is an obligate long-day plant. Is this much light needed to stimulate flowering? Well, certainly no. But this is a plant grown in the north. It needs cool temperatures but high light. And so basically by running these lamps 16 or 18 hours a day, they're able to increase the day-to-light integral and at the same time simultaneously deliver a long day. Likely it would be effective to deliver a long day to only operate maybe 1 every 4 or 1 every 5 lamps again, the minimum desired intensity is only 10-foot candles, so there wouldn't need to be too many of these high-intensity lights to achieve that. And this is a little more of a novel strategy. Growers have used some of their insight into how plants respond to light, and slowly but surely growers are starting to attach these high-intensity lamps onto an irrigation boom. And so basically the irrigation boom functions during the day when the plants need to be watered, but then at night the irrigation is not operating and these lights turn on. And so these booms will go back and forth across the crops multiple times during the night to serve as a way to provide cyclic lighting to plants. And this is actually a poinsettia, which again is a short day plant, and because short day plants are generally sensitive to cyclic lighting, this can be an effective solution. Now, there's really not a good commercial product for this type of boom lighting, and so basically what the grower has done their own sort of configuring of this. And anytime you do something where you're mixing the electricity with the water, you want to make sure that they're very careful about how it's wired. Perhaps a more safe and viable option would be to use something called the beam flicker. Again, that's a trade name for this high-pressure sodium lamp that has a reflector that basically rotates back and forth. And the reflector rotates 180 degrees to basically move that beam of light over a relatively large growing area. And so what we have here, and some research that we have done, is we have different distances from the lamp, and basically you have this lamp that goes back and forth and rotates. The mouse is a little slow here, but it rotates back and forth to the crops below it. Now, of course, the intensity delivered far away from the lamp is going to be much lower than the intensity delivered directly underneath it. And so some work that we have done is to basically quantify how much light is provided at these different distances from the lamp, and then what is the effect on the flowering of different crops. So here you can see a schematic diagram of that beam flicker in the middle where that light would be rotating back and forth. And the beam flicker rotates about 180 degrees once a minute. So here's basically the response that we observed directly under the beam flicker and then at different distances from the beam flicker. We have petunia, which this is a variety that eventually flowers under short days, but it's faster under a long day. We have petunia grown under a traditional 60-watt incandescent lamp, so low intensity, 10 to 20 foot candles. And then we have at different lateral distances from the beam flicker, this was a 600-watt fixture, and anywhere from 3 increasing up to 43 feet laterally from the beam flicker. And a general trend that we see is that the beam flicker is effective at inducing flowering, but at some point, once we get to 40 or so feet from that lamp, we start to get a delay in the flowering response. So some of these guidelines for controlling photoperiod, and especially to provide long days, is our goal is to provide at least 10-foot candles of light to bedding plants and perennials and those that are long day plants. In many cases, long days begin naturally in mid-April, so we would suggest providing long days until about that time. And then the last thing is that generally once a plant induces a flower, if it's moved to an unfavorable photoperiod, it will still continue to develop and flower. And so a guideline is that you can begin to light these young plants at the end of their young plant stage, and then during the finished stage until flower buds are visible. And then after that, if you want, you can have them turn the lights off, and flowering will still continue. Any questions on controlling photoperiod? Okay, so we're into the third part, energy-efficient temperature strategies during the finish stage, and I think you've already talked a little bit about this sort of concept in terms of how you can estimate fuel costs given different greenhouse situations. Well, there are lots of factors that influence crop timing, things like the maturity, as we talked about the day length. Vernalization is something where plants are given a cold treatment that can stimulate flowering. But really the major factor is the temperature that's provided to that plant. And then in some cases, the amount of light provided to that plant can also stimulate flowering, as we saw before with the seed impatiens. So what I'd like to do is basically give you a concept of how plants respond to changes in temperature. So what we have here is on the x-axis the average daily temperature in degrees Fahrenheit, and then a relative rate of plant development, where you have 0, which would be the plant is not developing, up to some maximum rate. Okay. So what we're going to do is then draw how plants respond to an increase in temperature. Basically, there's a temperature at which plants begin to grow, and that's referred to as the base temperature. And then above that base temperature, in this case that's about 35 degrees, as you increase temperature, the plant develops progressively faster. At some point then, it starts to grow as fast as it can, and that would be our optimum temperature. And then beyond that, the plant begins to experience stress and it actually starts slowing down. And once we get to some really warm temperature for a particular plant, that plant can experience so much stress that it begins to basically stop developing. And after an extended period of time at very high temperatures, that plant can actually die. So this is basically a schematic diagram of a typical plant's response to temperature. Now, between the base temperature and the optimum temperature, plants develop in a linear manner. So basically, with every degree increase in temperature, the development of that plant progressively increases between that base and the optimum temperature. So we have diagrams here. This would be what we would consider to be a cold-tolerant crop, a plant that will be growing beginning around 40 or so degrees Fahrenheit. And then we have crops that we would consider cold-sensitive. And these are crops that really would not develop until about 50 or so degrees, maybe high 40s to 50s. And so these are basically, you can start categorizing different plants based upon their sensitivity to low temperatures. So you'll see cold-tolerant crops will often begin to start growing somewhere in the between 30 and 40 degrees Fahrenheit. Cold-sensitive crops will often be between 45 and 52 degrees Fahrenheit. And not surprisingly, they often have they often have different optimum temperatures based upon their base temperatures. So what we have done over the last 4 or 5 years is looked at and quantified exactly how plants respond to different temperatures. And it's been kind of surprising how little data there was available on some of these very common plants. So what we have here is a French marigold grown under average daily temperatures all the way from 41 degrees Fahrenheit, increasing all the way up to 86 degrees Fahrenheit. And then we have the days to flower from transplant, and in this case, this was from a young seedling, approximately 3 weeks old. And you can see that basically as you increase the temperature, you get progressively faster flowering, as what we would expect. Now we can also then calculate at what temperature does the plant begin to develop, and although these did eventually flower, it was very slow, and so when we do some math, we predict that the base temperature is less than 45 degrees. Here's maybe a different type of example where we have clearly the plant does not do well at cool temperatures. In fact, those at 45 degrees or lower actually died from chilling injury. These barely survived. In fact, many of them did die. And then the plant really grew fast once it was grown at these warmer temperatures. So here the base temperature would be much higher than 45. It's probably going to be somewhere in the low to mid 50s, which again would be the temperature at which the plant just begins to grow. So unfortunately, not all plants respond the same, so we need specific data on how these crops respond. So here's a graph that shows the effective time to flower as a function of temperature. And so as you increase the temperature, the time to flower of vinca progressively decreases until some point where the plant basically is developing as fast as it can. Now we can then look at another crop. Well, before we do that, let's look at the effect of changing the greenhouse temperature. And this is something that growers kind of as an instinct did when the fuel prices were quite high several years ago. They lowered their temperature set points without thinking about the effect on their scheduling of their crop. So let's say that a grower originally was growing at 65 degrees Fahrenheit. You can see time to flower there is, about 55 days. If instead the grower reduced the temperature to 60 degrees, average daily temperature, in this case there would be a predicted 26-day delay in the flowering of that crop. So in this case, a very significant effect of a change in temperature in the time to flower. Now, wave petunia, you can see, is actually a crop that grows grows well at lower temperatures. And so if we look at the effect of that same 5-degree change in temperature, flowering time goes from about 40 or 41 days and is delayed only by about 13 days. So it's still a delay, it's just that the relative amount of that delay is less in this crop. And then if we think of a third example of a crop that's even less sensitive to temperature, a case here with French Marigold, going from 65 degrees to our example of 60 degrees, that would be only a delay in flowering of 6 days. So this illustrates basically the wide range that can exist in how different common bedding plants respond to temperature. So what we've done is basically, based upon our data, created this chart to categorize plants that are cold tolerant. Again, those would be ones in which if you're going to lower the greenhouse temperature, the effect on the flowering time is going to be less than the effect if you lower the temperature on a cold sensitive plant. So what we're encouraging growers to do is to begin to divide their crops based upon their response to temperature and grow cold-tolerant crops in one greenhouse, perhaps at one set of temperature conditions, and in separate greenhouses, grow these at warmer temperatures. Of course, this is a very incomplete list. There are dozens and dozens of more genera on which we need to get some better crop data on to categorize them under one of these different categories. So it's clear that temperature controls the rate of plant development. That's basically the accelerator on our card. It determines how fast do we get to a destination, or for the case of a plant, how fast does it grow to develop a flower. Well, we also know that daily light integral, or DLI, can influence flowering. It influences photosynthesis. It can increase the temperature of a plant. And as we saw before, under highlight, sometimes plants develop fewer leaves before initiating a flower. So if we're looking at precise scheduling of these greenhouse crops, ideally we consider the temperature, the photoperiod if it has a photoperiodic response, and the amount of light provided to that plant. So what we have done is basically looked at an interaction between light and average daily temperature to see how those two factors influence the crop quality and the time to flower. So here we have verbena. Photograph was taken 37 days from transplant from a seedling, grown under 5 moles of light. So this would be our darkest period of time in the winter. And as you can see, time to flower progressively decreases as the temperature increases. But note, however, that when these plants do eventually flower, the flower number is greater at the lower temperatures. Now, what if we grew these plants at the same temperatures but under much higher light? So here we have 13 moles of light, which would be just beyond our minimum desirable amount of light. And you can see that time to flower is faster. For example, if we look at 68 degrees, the plants flowered about a week earlier under the higher light. But also look at the effect on the flower number. We have 50% up to twice as many flower buds with the higher light. African marigold, we can see similar effects. You increase temperature under low light conditions, you get progressively faster flowering. Again, at the lower temperatures, though, you'll generally get a higher flower count. If we look at higher light intensities, here we're at 17 moles of light. Time to flower can be a little bit faster, but we also continue to see more flower buds under the higher light conditions. And I think the last example, just to illustrate some of the species-specific differences, wave petunia grown under low light conditions. You can see they're a little bit leggy, but they're in flower, and time to flower decreased rather dramatically with an increase in temperature. And when we had moderately high light conditions, you can see we got a little bit faster flowering, but still that general trend for increase in flower count and faster flowering with the warmer temperatures. So what we can then do is take some of this crop scheduling information and use the program Virtual Grower. Are any of you familiar with the Virtual Grower program?
No, sir.
Okay. Basically, it's a software tool available free for growers. It's a program developed by the USDA. It can be downloaded on your computer, and it's a neat way to basically understand how different parameters of a greenhouse or a growing temperature or other factors can influence the amount of energy consumed in a greenhouse. So of course we know that energy costs to heat a greenhouse depend upon where the greenhouse is located, the greenhouse characteristics, the time of year, the efficiency of their boilers, et cetera, et cetera. So this is available free at virtualgrower.net. What we've done is use this program to estimate some fuel to estimate some energy costs by growing these plants at different temperatures. So here's basically a screenshot. When you open, actually this is an older version of Virtual Grower, but it's improved actually since it was released. But basically you enter some of the dimensions of your greenhouse, the materials, what it's made of, how it's oriented, different parameters for construction, fuel types. There are lots of different fuel types, the price, where is the greenhouse located, and actually the newer version, which I need to update, has a lot more options in terms of what sort of heater do you have, how many gaps are there in the glazing, other things that basically will help you calculate their exchange rate. Here is an example of where you can do some fine-tuning for a greenhouse, so you can pick different materials for the roof, for the sides, if it has a knee wall, what are the dimensions of the greenhouse, how many spans, what's the shape of the roof, etc. So the idea is to build your greenhouse virtually. So if a grower has a certain greenhouse, they'll basically know all of these characteristics, and the idea is to enter that information into this program. And then once you've done that, then you can create a heating schedule. So when do you start to heat, at what temperature, do you have a different day versus nighttime temperature, etc. And then the output, again, there are some more options to this in the newest version, but basically it will give you then, based upon all of the inputs that you've put in here, based upon historical weather data from the location that you selected earlier, and all the other factors, it will then estimate what that heating cost will be for that production space for a particular month, and then it will also be provided by the cost on a per square foot basis. So basically you can use this sort of program to get some estimates about heating costs, and then let's say that you're going back, in this case, let's say that this was at 68, 63 day-night temperature. You could then go back and say, well, what if I want to grow 5 degrees cooler? What's the effect? You could change this to 63, maybe this to 58, and then click to your other screen and then see how that heating cost would change. It's a very useful tool. It's developed with greenhouse growers in mind, so the intent is to basically make it as user-friendly as possible. So what we've done is use that program to look at heating costs for different crops. In this case, we have Petunia Wave grown at different temperatures for 2 finished dates in Madison. These are just a variety of assumptions. Some people have some challenges or concerns with some of our numbers, but we have to start somewhere, and of course things are always changing. But we look at heating costs to heat about a ½ acre of greenhouse with a double poly roof. And what we can then do is look at how does temperature influence crop timing, and then how does that period influence be consumed. So what we have here is petunia, and the goal is to have flowering in the 1st of April. So there are different ways we can have flowering for the first part of April, and it depends, of course, upon at what temperature are we going to grow. So if we grow at an average temperature of 58, it can take a long time for the plant to flower, in that case 64 days. But then as you increase the temperature, the average daily temperature, you can see that the plants can be transplanted later and later in the spring to achieve your April 1 finish date. So then the question is, how much energy is consumed by growing it at a cool temperature for a long period of time versus growing progressively warmer but for shorter periods of time? Well, here's the photograph we saw earlier. We assumed an average daylight integral of 10 moles of light, so we're basically saying we're not in a very light-limiting situation. We're providing long days, which promotes flowering, and we can calculate the heating costs to produce this crop at different growing temperatures using Virtual Grower, and we can see that basically the lowest amount of energy is being predicted to be consumed by growing that plant at a relatively warm temperature for a short period of time. And what really is more expensive is if you grow the crop cold, production of that crop is delayed so much that you're heating it for such a long period of time, you're consuming more energy to produce that crop. Now, these are some values for later on in the spring. In May 15, of course, the prices decrease substantially. And what we typically find is the effective temperature on total energy consumed for heating has less of an effect for later spring sales than it does earlier spring sales. Now, I think the last thing I want to talk about here is the concept of temperature integration. I think most growers are already using this concept, but the idea is how we deliver a particular temperature can have an effect on the amount of energy consumed. So plants integrate temperature on a daily basis, and so they will grow and develop at about the same rate if they are grown at a 65-degree day-night temperature, or if the day is 60, the day is 70, the night is 60, or vice versa, and that's assuming these are each 12 hours long. So they basically grow and develop in response to the average daily temperature. So we know that most of the energy for heating occurs at night, and therefore it stands to reason that a cooler night and warmer day can consume less energy while still achieving the same average daily temperature. One small downside of this is that when we have a positive day temperature versus the night, that's something that creates what we know as a positive diff. Growers will describe the difference between the day and night as a diff, and that can have an effect on how plants extend, how the stems extend for sensitive crops. So a very dramatic example is when we have a cool night and warm day, we get a short plant or a negative diff condition. When we have a warm day and a cool night, although that may consume a lot less energy, because we have a cooler night, you can see that that also promoted stem extension, in this case on Easter lily. So one of the things we need to be concerned about is that this diff tool has been used as a strategy to produce compact plants. However, the downside of a negative diff is that it actually consumes more energy. So what we've done here again is use Virtual Grower with different assumptions to look at provide different ways of providing a 65-degree temperature using a warmer day than night, the same day than night, versus a cooler day than night. And you can see that compared to the positive diff conditions, the negative diff conditions were more expensive. So this just illustrates kind of the trade-off between a negative diff and a shorter plant versus a positive diff. Less energy is consumed, but the plant may be a little bit taller. So these are just the different temperatures for to achieve these different diff conditions. So basically, we've looked at different things that Virtual Grower can do. It can help estimate fuel costs given lots of different factors, whether it's on a daily basis like we see here, or whether it's different crop timing timing information and different growing temperatures, and looking at how much energy is consumed over a period of weeks or months. Last slide is we have more resources for information focused primarily on different crop strategies, cultural strategies to produce crops efficiently. But we also, on that website, have information on other topics related to energy. Almost all that information is from academics. We try to make sure that it's not a biased source of information. And so we'll have things focused on crops in particular, or it could be in some cases on some technologies and some of the pros and cons, looking at some technologies for improving greenhouse efficiency. So with that, I'd like to thank you for those that have stayed on and may have time here for a few questions.
Eric, I just want to put in, you didn't do a plug for your book. Eric and Paul Fisher did a book called Lighting Up for Profits, and I believe is it available from Ball, or who's publishing it?
You know, it was, but they're mostly out of the book business, so now it's Meister Publishing.
Meister Publishing. But it kind of goes through some of the arguments here on lighting and talks about different plants. And it's a fairly nice reference.
Thanks. Yeah, that's a good point. I should have included that.
So if you do a Google search, you should be able to find that if you want it. And it comes with a CD too. Does anybody have any questions?
Yeah, Scott, this is Kevin.
Yeah.
Kevin Spooner. A few weeks ago, I had a discussion with a couple growers that were in the room about light tubes and mirrors and light intensity, and it was kind of just a what-if scenario discussion. But the question was, why don't we use our natural sunlight and just intensify it using the same concept in a light tube. You put a tube in and it lights up the whole room. And I guess the question was, is that enough to grow plants? Or is it, well, anyways, just a comment on using mirrors or other ways to intensify natural light into a greenhouse.
Well, I suspect that with our traditional greenhouses, we probably couldn't do that very well. But if we use a brace-type, passive-type greenhouse, then you could put reflective materials on the ceiling to reflect some of that sun. But I don't know if even then you'd get enough light level. I don't know. Eric, do you have any experience with that?
Well, not firsthand, but I know some folks at Minnesota about 10 years ago looked at, I think it was 3M was going down the road of trying to put reflectors on the roof at the top of each roof and pushing light down, and they found basically that the amount of light that they were able to reflect, it then casted a shadow that offset basically the gain. The shadow of the greenhouse right next door, or the greenhouse the next bay over. So there basically wasn't a net gain.
Okay.
Now, there were some folks in Arizona who were interested in trying to take light and funnel it down into a growth chamber. And they were successful. It was just really expensive to do. And you think about the cost to do that versus just put artificial lighting, and the artificial lighting came out ahead.
Yeah, I know somebody had sent me some samples of something that you actually stuck on the roof, and it provided shade during the summer, but reflected light in during the winter. But yeah, I don't think it ever caught on.
Yeah.
So probably, Kevin, your answer probably is it's probably not very cost effective. Supplemental lighting would probably be better.
Well, that's what we figured, but it was just some creative thinking going on, I guess.
Yeah.
Any other questions?
Well, if there's nobody who's got and I apologize if this is too simplistic, but this topic on lights and heat and whatnot, this is a question I got from a local school who's growing corn in their school greenhouse for a school play, and they want to know what the maximum settings might be to get that corn up as tall and lush as possible in a short period of time. And I'm assuming it has to do with daytime or temperature and light duration, but I didn't have a real good answer for him.
Yeah, well, yeah, you need really high temperatures for corn. So, you know, if they want to get it going fast, I'd go at 75 or 80 degrees. And, you know, they can handle all the light you can give them. So,
you know who you might get a hold of, Joe Lauer?
Yeah, I guess I asked Joe already, but he didn't really take the time to answer my question.
Then why don't you try Sean Kepler?
Okay.
One of those guys must be growing corn in the greenhouse for trials.
Mm-hmm.
So I'm sure one of them could give you an idea what they're doing.
Okay, all right.
I see the corn growing over in the research greenhouse.
Mm-hmm. Well, you just picture the crop growing in June. It's longer days. We got warmer temperatures. I mean, you try to simulate that as much as you can, I guess.
Yep. Depends how tall you want it.
Mm-hmm.
yeah.
So.
All right. Sorry for the real simple questions.
No problem.
I did enjoy your presentation. I haven't heard some of this stuff before.
Oh, good. Thank you.
Any other questions? Well, hearing none, I guess we call it a day.
Okay.
Thanks very much, Eric.
Thank you, everyone. Yeah. Have a good day.
And we'll talk to you again soon.
Sounds good. Thanks.
Yep.
Bye.
Thanks again, Scott. This is a great series.
Great. Glad you enjoyed it.